This lesson is about graphing polynomial functions. Now, we've already talked about polynomials. What we're going to do today is we're going to learn how to look at a polynomial, look at different elements of that polynomial function, and then be able to graph it just based on the function. Okay, so let's first go through the definition of a polynomial function. First, we know that a function that can be written in the form f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus, and then there's a bunch of other terms, a sub 2 x squared, a sub 1 x plus a sub 0 is a polynomial function. So let's break this down a little bit. We know that we have real number coefficients. So our coefficients are the numbers out front, the a sub n's. Those are our coefficients. So a sub n, a sub n minus 1, a sub 2, a sub 1, all the way down to that last value. These are my coefficients. Okay, n is a non-negative integer, so it's like a counting number, 1, 2, 3, 4. And a sub n is not going to equal 0. When we say, and then 2, I should say, if it's a non-negative integer, it's not a fraction. So our leading term, the coefficient of our leading term, so our leading coefficient will be a whole number. Where else? And where are we in this definition? And that is the definition of a polynomial function. So that's my next blank here. In standard form. The domain of a polynomial function is always negative infinity to infinity, because remember, polynomial functions are smooth continuous curves. So I could have a polynomial that looks something like this. Okay, I could have something that looks like this. I have a polynomial that looks like this. Okay, that's a quadratic. So smooth continuous curves. So the domain is always going to be negative infinity to infinity. The degree of the polynomial function, so the degree is n. So when I go back to the standard form here, my degree is n. So if I want to know what degree this polynomial function is, if the first term is something like 7x to the 32nd power, the degree of the polynomial is 32. The leading coefficient, so we'll go through a lot of vocabulary here. The leading coefficient, so that's the number in front of the leading term, is a to the n. So my leading coefficient, a to the n here. And the leading term is a to the n times x to the n, okay, which is my leading term. I have a lot of drawing going on here. So my leading term, let's see if I can use the highlighter. So the highlighter will highlight this leading term, okay? So the leading term is made up of that leading coefficient, a sub n, and then the degree of the polynomial is determined by the degree of the leading term. Okay, so now that we've made our way through the definitions, let's go through and look at some of the polynomial functions. So for each of the polynomials that are given here, we want to write the polynomial in standard form, and then we want to determine what the leading term is and what the degree is for each of the functions. Okay, so the first one is f of x equals 7x times 5 plus x. Now to write this in standard form, I'm going to have to distribute the 7x. So it'll be 7x times 5, which of course is 35x. 7x times x is 7x squared. Standard form, highest degree is always first. So f of x equals 7x squared plus 35x. And then I'm supposed to determine, let's make a note here that this is our standard form. And then I'm supposed to determine the leading term and the degree. So the leading term is 7x squared. And the degree of this polynomial is 2. This is a quadratic. If I asked you for the leading coefficient, just to practice with some of our new terminology, the leading coefficient is 7, and I get that from the leading term. Okay, so for B, g of x equals x times 2x minus 4x squared plus 3x squared. do this one yourself. Write it in standard form, determine the leading term, the degree, and go ahead and find the leading coefficient, and then come back and check your work. Okay, so you're back. So for your answer for standard form, once we distributed the x and then combined like terms, you should have found that g of x is equal to negative 4x cubed plus 5x squared. Make sure that the negative 4x cubed is first, because we always write the highest degree first. Leading term, of course, is negative 4x cubed. The degree is 3, it's the third degree polynomial, and then the leading coefficient is negative 4. So the leading term of our polynomial is going to tell us so much about the behavior of the graph. It tells us what happens, what the end behavior is. So as x approaches positive infinity, what does the graph do? As x approaches negative infinity, what does this graph do? I know that these polynomial functions are smooth, continuous curves with domains of negative infinity to infinity, so they extend on forever, but I want to know what happens at the ends of these graphs. And so we're going to determine that, we're going to look at that leading term of the polynomial, and then we're going to look at the degree of the polynomial and the sign of the leading coefficient, and that's going to give us more information too about the end behavior of these graphs. Okay. So there's a lot that you can do here. You can memorize these, but I really am not a fan of memorization, because then what tends to happen is, you know, a week down the road or after you take the test, you lose it. And so it's just not a good way to learn material, to learn new material that you can then apply later. So what I like to do is I like to teach this from the perspective of something you already know, something that you're already familiar with, and then we can apply those same principles to other polynomials. So that's what we're going to do here. So on the left, we're going to talk about if the degree of n is odd, and then the scenarios on the right, we're going to talk about, well, what about if the degree of n is even? All right, so let's begin with what about odd degree polynomials? Well, the odd degree polynomial that you are most familiar with at this point in the semester is a cubic. Okay, so let's just use a cubic. So we're going to say, okay, what about f of x equals 7x cubed? We know what a cubic looks like, right? And so I can use that to start to break this down. So in my scenario here, I've got an odd degree polynomial. 3, of course, is odd. And if a to the n is greater than 0, that's my first scenario here. So a to the n, that leading term is greater than 0. Now my leading coefficient, I should say. My leading coefficient is 7. So 7, of course, is greater than 0. So that tells me that in that scenario, as x approaches positive infinity, y is going to go to infinity. And I know what a cubic looks like, right? It goes something like this, okay? So in this scenario, I've got 7x cubed, and it's going to behave something like my graph here, okay? And so as x approaches positive infinity, then y is going to approach, so as x approaches positive infinity, then I know that y, I'm going to write this a little bit differently, I think it makes more sense, that y will also approach positive infinity, okay? And then as x approaches negative infinity, I'm just going to rewrite this here, then y will approach negative infinity. That's my end behavior, okay? And that's for a cubic. I'm used to dealing with a cubic. Now this holds true for any odd degree polynomial when the leading coefficient is greater than 0. So when the leading coefficient is positive. The only thing that changes is in the middle here, instead of having this smooth curve like I've got, I get some more lumps and bumps. So maybe if I had something like, we'll just make something up, f of x equals 42x to the 17th plus 16x cubed plus 4. I have no idea what the graph of that looks like, but I know that the leading coefficient is positive. I know it's odd degree. So the ends are going to behave just like a cubic's ends behave. And then because I've got this degree of 17, I'm going to have as many as 17 max and mins here in the middle. I'm not going to draw all those, okay? But right now, I don't care about what's going on in the middle. I only care about that end behavior. So if you'll focus on what you know, which is what a cubic looks like, then it'll allow you to figure out the end behavior for any odd degree polynomial. Okay, so let's go on. What about if that leading coefficient, instead of being positive, is negative? Well, that's my scenario here at the bottom. So my leading coefficient now is negative. So let's make up a scenario. So we can use our same example. So maybe f of x, instead of equals 7x cubed, is negative 7x cubed. Again, I know what a cubic looks like, okay? Well, with the negative out front, think about transformations. Think about what you know about transformations. That's the value of c out front. And I know when I have a negative value multiplied out front, then I reflect over the x-axis. So what I've done is I'm going to take this graph of a cubic. Let me just sketch it on here. I'll take my normal graph of a cubic and I'm going to reflect it over the x-axis. Okay, I'm going to erase this so we don't get confused. Actually, let me just do it. And so if it's been reflected over the x-axis, then what my graph is going to look like is this. Okay, and so it's still that graph of a cubic, but it's been reflected over the x-axis. And so now what I know is as x approaches positive infinity, well, y is headed to negative infinity. And as x approaches negative infinity, then y approaches positive infinity. So the ends are going in opposite directions, and that leading coefficient tells me, is it what I think of as the regular shape of a cubic, or is it one that's been reflected over the x-axis? Okay, and again, if this was any odd degree polynomial with a leading coefficient that's negative, so a negative number out front, then I have that reflection, and this same pattern will hold true. Okay, so let's look at the even degree scenarios now. So the most common even degree polynomial that we work with is a quadratic. Okay, so let's not choose something more difficult. Let's choose something that's easy for us to understand. Okay, so let's assume I have a quadratic. I should probably include f of x in here. Okay, so f of x equals 2x squared. Now that's a quadratic that opens how? Well, you can look at that leading coefficient. Now in standard form, that leading coefficient is a. We have ax squared plus bx plus c, and we know when a is positive. So in this case, our a value is positive, so greater than 0. That's positive. Well, we know that that's a quadratic that opens up. So it looks something like this, okay? And so again, if I want to write my summary of what my end points do or what my end behavior is, then as x approaches positive infinity, I can see that y approaches positive infinity here. And as x approaches negative infinity, then y also approaches positive infinity here, okay? And so that's my end behavior. And so this holds true for any even degree polynomial. So again, I could have an even degree polynomial like, I don't know, maybe I've got 14x to the 24th power. 24 is obviously even. Then what I'll have is I'll have as many as 23 max and mins in here, but the end behavior will be exactly the same. Okay, and so all I'm concerned about at this point is what does this polynomial do at the ends? What does it do for very, very large values of x as x approaches positive infinity? And for very, very small values of x as x approaches negative infinity? Where does y go? Where do the ends of the graph go? That's what I'm looking for here. Okay, and then finally my last example. So again, I'm going to stick with a quadratic. So f of x equals negative 2x squared. Well, now that leading coefficient still is negative, so a is less than 0. And I know from my work on quadratics, when a is negative, that I have a quadratic that opens down. So you get a scenario that looks something like this. So as x approaches positive infinity, so very, very large values of x, y goes to negative infinity. And I can see that here on my ends, okay? And then as x approaches negative infinity, y goes to negative infinity. So you can see for your even degree polynomials, the ends are going to go in the same direction. Okay, they're either both going to go up if the leading coefficient is positive, or they're both going to go down if the leading coefficient is negative. Okay, and then for my odd degree polynomials, the ends are going to go in opposite directions. They're going to go like the shape of a cubic when we think about a normal cubic that hasn't been reflected. If that leading coefficient is positive, and then it'll look like a reflected cubic if the leading coefficient is negative. So that's sort of a precursor to what's coming up in my notes here. Okay. All right, so let's see what we can do if I just give you the function. Can you tell me what the end behavior of the graph is? So for the first one, f of x equals -1/10 x cubed plus 5x squared minus 3x plus 2. And I want to know what's the end behavior. What happens for very large values of x? As x approaches positive infinity, where does y go? As x approaches negative infinity, where does y go? Okay, so the first thing I need to do is I need to identify the leading term. So the leading term is -1/10 x cubed, okay? And so my leading coefficient is, of course, negative. And my degree is 3. So this is an odd degree. So this is an odd degree polynomial. So you need to start to think in terms of a cubic, in terms of how a cubic behaves. And so when I'm looking at this graph, I don't even have to worry about where the points cross or anything else. Not yet anyway, that's coming. Because the leading coefficient is negative, I know that it's going to behave a cubic that's been reflected. And then I'll have, some other activity here in the middle. I don't know what this is. In fact, don't take that to heart. But what I do know is I know how the end behavior is. I know what the graph does at the ends. And that's what I care about. So what this means is as x approaches positive infinity, y approaches negative infinity. And as x approaches negative infinity, so very small values of x, y approaches positive infinity. That's the summary of my end behavior. Okay, let's look at b. F of x equals 150 x cubed minus 200 x to the fourth plus 500 x squared. Now the first thing I need to do here is I need to write this in standard form. And standard form is highest degree first. So negative 200 x to the fourth plus 150 x cubed plus 500 x squared. Now I can look at that leading term, which is negative 200 x to the fourth, and that's what's going to tell me, and that's what's going to dictate my end behavior. Again, my leading coefficient is negative 200, so obviously that's negative, and my degree is 4. So I have an even degree. Because it's an even degree, I know that it's going to behave like a quadratic behaves. The ends are going to go in the same direction. They're either both going to go up or they're both going to go down. Well, because that leading coefficient is negative, then that tells me that they're both going to go down. Okay, so I'm going to have a bunch of other stuff going on in the middle here, whatever this looks like. But the end behavior is what I'm concerned about. So as x approaches positive infinity, y approaches negative infinity, and as x approaches negative infinity, y also approaches negative infinity, going in the same direction. Okay, so what I'd like you to do for C and D is I'd like you to take a shot at those yourself. And then when you've got C and D both done, come back to the video and check your work and let's see how you did. Okay, so you're back. So hopefully you've got your answers here for C and D. So for C, you should have gotten the simplified function in standard form was 4x cubed plus 5x squared. Leading term, 4x cubed. It's an odd degree polynomial. Leading coefficient is positive, so it's going to behave like a cubic. So as x approaches infinity, y approaches positive infinity, and as x approaches negative infinity, y approaches negative infinity. Part D, you'll need to rewrite it to get it in standard form with the highest degree first. So g of x is equal to 0.5 x to the 6 plus x cubed minus 7x squared plus 12. Leading term is 0.5 x to the 6. That's an even degree polynomial with a positive leading coefficient. So this is going to behave like a quadratic where a is positive, so it opens up. So that means that as x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y approaches positive infinity. So you can see when it's an even degree, ends are going to go in the same direction. When it's an odd degree, the ends are going to go in opposite directions. So now we're ready to start putting all this information together so that we can graph a polynomial. First, we're going to do a bit of review from Module 2. So we know that the root form of a polynomial function f with n roots is a times, so remember a is that leading coefficient, a times x minus root 1 times x minus root 2 times x minus root 3 all the way up to x minus root sub n, where the leading coefficient a is a non-zero real number. And then the number of times that a root appears in the list of roots is what we call the multiplicity of the root. All right, so when we graph our polynomial functions, we're going to begin by writing the function in root form. That's going to help us. Then we're going to determine the coordinate of the y-intercept. And remember, the y-intercept occurs where x equals 0, so we're going to evaluate f of 0, and that'll give us our point 0, and then whatever the y-intercept is. And then we're going to determine the real roots. Remember, the real roots are where it crosses the x-axis. Those are our x-intercepts. So the graph of a polynomial function crosses the x-axis if the multiplicity of its root is odd. It will cross, and it touches but does not cross, or it bounces off the x-axis if the multiplicity of the root is even. We're going to use the leading term to determine the end behavior. That's what we just did in our previous work. So what happens as x gets really, really large in the positive and negative directions? So as x approaches positive infinity, where does y go? Okay, and as x approaches negative infinity, we want to know, where does y go? Okay, that's what we're looking for, that end behavior, and we're going to use that leading term to determine that. And then finally, we'll create a rough sketch of our graph using all of the information in the first 4 steps, and we'll plot any additional points that we need. So always remember that you're going to find these particular points in every one of your graphs, but if you need more points to create a better graph, then plot more points. You can plot as many points as you want. This is just the minimum number of points. Okay, so let's start with our first example here, A. H of x equals negative x minus 5 times x minus 4 times x plus 1. Now, this has already been given to you in root form. Wasn't that nice? Because I could have made you factor this, but it's been given to you in root form. So I need to determine what's going to happen in each one of these roots. So I know I have a factor at x minus 5, which means the root is positive 5, and the multiplicity I can see is 1, because this is understood to be to the first degree. In fact, each one of these is understood to be to the first degree, okay? So with a multiplicity of 1, that means that my graph crosses, because remember, the multiplicity is odd, so the end's going opposite direction. So it crosses the x-axis at that point at 5, 0. That's my x-intercept, okay? So next, my next factor is x minus 4, which means my root is at 4. Again, the multiplicity is 1. So that tells me that this is going to cross the x-axis at the point 4, 0, at that x-intercept. And then finally, my last factor is x plus 1, which means the root is negative 1. Multiplicity again is 1. So it's going to cross at the x-axis at -1, 0. Okay, so I already know a good bit about how this graph is going to behave. So let's go ahead and put our roots on here. So I've got -1, and then 4, and finally 5. And I know that each one of these is going to cross the x-axis. Okay, I'm not ready to draw my graph just yet. I need a little more information. Next thing I'm going to look at is I'm going to look at my leading term. So my leading term is -1x cubed. Now, where on earth did I get that? Okay, remember the leading term comes from the standard form. So I know that if I multiplied all of these terms together, remember I'm only looking for the leading term. The leading coefficient is -1, and then x times x times x is x cubed. The rest of it, I'd have a whole long string of a polynomial after it, but I don't care about any of that. I only care about that leading term. So my leading term is -1x cubed. So that means this is going to behave like a cubic, but because it's negative, the leading coefficient is negative, it's a cubic that's been reflected over the x-axis. So when I'm looking at that end behavior, that means as x approaches positive infinity, y approaches negative infinity. And as x approaches negative infinity, y approaches positive infinity, opposite directions. So I'm going to draw just some little markers on here to remind me of what's going to happen for my end behavior. Okay, so just putting together some more of my clues here. And then finally, I need to look at my y-intercept, where x is equal to 0. That's the last piece of information I need here for my graph. So my y-intercept, and that of course occurs where x equals 0. So I'll evaluate h of 0. So everywhere there's an x, I'm going to put in a 0. So this is negative. 0 minus 5 is -5. 0 minus 4 is -4. 0 plus 1 is 1. Negative times -5 is +5 times -4 is -20 times 1 is -20. So my y-intercept is at 0, -20. So I'm going to have to do some scaling on my graph here because this is never going to work otherwise. So I'm thinking I'm going to scale these by 2. That'll work good, okay? And so I have a point at 0, -20. Okay, so now I have enough information to sort of play connect the dots here. It's like when you were in first grade, okay? I can see what the end behavior is. I know that through each one of my x-intercepts, which are my red dots, that it's going to cross through because my multiplicities were 1. And then I also have to intersect the y-intercept at 0, -20. So let's see how well I can draw here. Comes down through the y-intercept, back up. I have to go through this through this x-intercept, and then I have to turn and come back down through my other x-intercept and then down. I have sort of an extraneous line over here I'm going to get rid of. And that's my graph, okay? Now, if you wanted more points than that, maybe you wanted to know how high that peak there was, then you could graph a point at, you could check at 4.5, what's the value of this polynomial. But we're not looking for an exact graph here. We're looking for something pretty good, and this is pretty good. But we're not looking for, it doesn't have to be exact, it doesn't have to be perfect, it just needs to be really close, okay? So if that makes you uncomfortable, you plot as many points as you want. So that's the graph of h of x, and all I used were my roots, which gave me my x-intercepts. I looked at the leading term, which told me what the end behavior was, and I looked at the y-intercept to see where it was going to cross the y-axis. Now, as a little bit of an aside here, I will tell you this. Sometimes you guys give me graphs that snake back and forth all over the place. Don't do that. You know that this graph only has 3 x-intercepts. So you should not cross the x-axis in any more than 3 points, okay? You know that this graph has 1 y-intercept and it's at 0, -20, which means you should not cross the graph at any additional points on the y-axis. Okay, so don't all of a sudden start snaking back and forth and up and down and crissing and crossing all over the place, because if there was additional x-intercepts, you would have found them, and if there was an additional y-intercept, you would have found it. Okay, so this is what your graph looks like. Okay, so for this page, we've got 2 more problems. They're a little more evolved, they're a little more advanced than the one we just did. But what I would like for you to do is I'd like you to pause the video and I'd like you to at least try them. Even if you struggle a little bit, that'll be okay, because you can come back and you can listen to me explain and you can make some adjustments to your graph. But you might surprise yourself and you might be just okay. So go ahead and pause here and then come back when you're finished with B and C and we'll talk through the answers. Okay, so let's see how you did. So with B, you should have found that your factor was x plus 2, which means your root was at -2. Multiplicity of 1 tells you it's going to cross at -2, 0. Ends are going to go in opposite directions because the multiplicity is odd. Remember, odd multiplicity, opposite directions, they both begin with an O. Your other factor was x minus 4, which means the root is 4, multiplicity is 2. So even multiplicity tells me it bounces. It's going to touch the x-axis and then it's going to come back up in the same direction, and that'll happen at 4, 0. Since the leading term is -2x cubed, it'll behave like a cubic that's been reflected over the x-axis. And so as x approaches infinity, y approaches -infinity, and as x approaches -infinity, y, of course, approaches positive infinity. Finally, for the y-intercept, you'll evaluate p of 0, and you'll get the point 0, -64. Now, to graph this, we can use 1s on the x-axis. That's going to work, but we're going to have to scale our y-axis. Now, just as a bit of an aside, sometimes you guys give me some wacky scales, okay? So just make sure that you're being consistent. If you tell me, let me do this, I'll do this in red. If you tell me this is 10, then this can't be 50, okay? So if you've told me this is 10, that means each block is 10, okay? And then this all of a sudden can't be 70. It's like you guys make up some crazy stuff sometimes. So don't do that. Let me erase all that madness. Okay, so I have scaled mine by 10s, you can see, and you could have scaled by 5s. You'd have been a little bit off the graph, off the grid a little bit, but just make sure your scale is consistent. And so you can look at your graph, see if it matches. Everything should look the same. And so you can see you crossed at -2, 0. That's where the multiplicity was odd, and you bounced at 4, 0. That's where the multiplicity was even. And then, of course, your ends matched what we found based on that leading term. Okay, so for the next one got a little more complicated. Begin by looking at your factors. So remember, so our first factor here, hopefully you got this one, was x, okay? X. So that means the root is 0. Multiplicity is 1 because this is understood to be to the first degree. These are all understood to be, well, that's to the first degree. This is obviously to the third. This is to the second, okay? So multiplicity is 1, so that means it's going to cross at the point 0, 0. For the factor of x minus 2, the root is 2, multiplicity is 3. It's going to cross, but this time, be careful with this, it's going to cross like a cubic. So make sure you have that little bit of a bend in there. I'm not sure which way if it's a regular cubic or if it's one that's been reflected. We'll get to that in a second. But just make sure that when you graph this, you get that little bit of a bend in there around that root. Okay, it doesn't cross straight through like a line. It would cross straight through like a line if the multiplicity was 1. My next factor was x plus 3. Multiplicity was 2, so that means it's going to bounce. It's going to behave like a quadratic. I don't know if it's going to open up or down, but it's going to bounce off of the x-axis. All right, next thing we look at is the leading term. Leading term was -3x to the 6th. Now, where on earth did I get that? Well, remember, I've got -3x. This is to the first. And then x minus 2 is to the third power. X plus 3 is squared. So remember, when you multiply exponents, or when you multiply values with exponents, you add the exponents. So 1 plus 3 is 4, plus 2 is 6. That gives me that 6th degree polynomial. Okay, so this is going to behave like a quadratic because the leading coefficient is negative. It's going to be reflected. The a value is negative. It's going to open down. That's what I found here. And so as x goes to positive infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity. Y-intercept, you're going to evaluate h of 0. Your answer is 0, so your y-intercept is at 0, 0. Now, I don't really have a ton of information, and I don't know exactly how this graph behaves in terms of between the x-intercepts. How high does it go? What are those values? It might be nice to know so I can get a graph that is as as accurate as possible. So if you need some more points, graph some more points. And so that's what I did. I evaluated h of -1, and the value is -324. And I evaluated h of 1, and the value is 48. So based on that, I scaled my axis. Okay, each of my blocks was worth 50. And so that'll give me a graph that's much more indicative of what's going on here. As a matter of fact, I probably should fix a small part here. It doesn't come down quite this far. So I need it to go to -324. So something like that. Okay, a couple things to point out here. Make sure that your graph is behaving appropriately around your x-intercepts. I know that at -30, it was supposed to bounce, and it does. It behaves like a quadratic here. At 0, 0, it's supposed to cross through, kind of like a line, and it does. Now, this is the one that's really important because I look for this when I grade. At 2, is it at 2, 0? Yes, at 2, 0, it needs to behave like a cubic. And so you can see I get that little bit of a bend here in my graph. So make sure when you sketch that graph that you've got that behavior so I can see that you know that it was a third degree polynomial and it's going to behave like a cubic around that root. So make sure you make that really, really clear.